Hi there, welcome to this lecture series on matrix algebra. Today we cover lecture 12. This is part 1. The topic is the rank of a matrix. We will go through special spaces formed by a matrix, such as the row space and column space, and some special spaces that we call null space. And then we'll talk about basis, and then we'll talk about the rank of a matrix. Okay, so let's get started. Let's first introduce the row space and the column space of a given matrix. Given a matrix A in R m by m, meaning I'll have m rows and n columns, as we write here. So a matrix can be represented by collection of m row vectors u1, u2 to um, and at the same time I can also view it as a collection of the column vectors v1, v2 and vn. Then we can use these vectors to form spaces by forming a span of it. So if you take the row vectors u1, u2 and um, there are m of them, and you form a space by collecting all possible linear combinations of them, then this is called the row space. So this is the set of linear combination of row vectors in this form. So c1 u1 plus c2 u2 plus cm um, where all the coefficients c's are just real numbers. So in the end, this will be a vector of length n, so therefore it's a subspace of Rn. Similarly, you can also take the column vectors v1, v2 to vn, and then you form span of it, and this becomes a space, and we call that the column space of A. Okay, so that's a linear combination of all the column vectors, so we can call this like c1 v1, c2 v2, and cn vn, sorry for the typo. And then the coefficients c's here are real numbers. So in the end, this will be a column vector of length m, so it's a subset of Rm. Okay, let's take a immediate example following this definition. Consider a matrix which is 2 by 3, which looks like following. So we can view this as collection of 2 row vectors. One is the first row and the other is the second row. And also you can consider this as a collection of 3 column vectors, 1, 2, and 3. Okay, so to form the row space of A, we take the 2 row vectors, these two, which are here, and we take the span of it, and then this will be a subset of R3 because it has 3 elements in the end. And if you write out a linear combination of these, that will be C1 times the first row plus C2 times the second row, where C1, C2 are real numbers. And the column space of A is totally similar. We take the 3 column vectors and we form the span of it, and this will be, in the result, it will be a vector, any vector of length 2, and that's a linear combination of these 3. So it will be in R2, and you can also write it in this way with coefficients C1, C2, C3, and linear combination. Here the C1, C2, C3s are just real numbers. Okay, so to write out a form of a row space and a column space of A, just like per definition, there is really nothing, but the properties of these spaces are far more intriguing and they're important. Okay, so let's consider a linear system, and we want to make a connection of this linear system with the column space of A, which we just defined. So I have a ax equal b. That's my system, and A is a matrix, and I can consider this as a collection of column vectors v1, v2, and vn. And then we can write out the system, write all the elements in A times the x, the unknown vector, equals the b, the right-hand side. So we see that we can expand this ax equal b and write it out as m equations, write out the product. So this matrix times this vector equals that. So this row vector times this column vector, and the product of it will give me a number that's b1. Okay, so if you work that out, so it will take the form x1 a11 plus x2 a12 so on, add all up as the first element, and then the rest is all similar. Okay, that shall equal b. Okay, and then let's take a closer look at this vector here and each element of it. If we look at like the first term in each of these elements, we see that x1 appears in all of them. So I can take out the x1 and then collect the rest as a column vector. Then I look at the second entry in each of these elements and then do a similar thing and take out x2 and keep the rest. And so on and so forth, and all the way to the last one that I can take out xn. It's a common term, and then collect the other a's. So this product can be viewed as take all the column vectors of A and make a linear combination with coefficients x1, x2, and xn. And we want this linear combination in the end to equal to this b vector that's given. Okay, now we can view the solution of a linear system in the following way. So if I want to solve ax equal b, then this is equivalent to the following problem. That is, given a column space v1, v2 to vn, and I am given the vector b, and then I want to find a way that is a linear combination of all these v vectors such that they add up to be b. And the coefficients of this linear combination is the solution of my problem, is the unknown. Okay, so twist the mind a bit and think a problem in another way, equivalently. Okay, so here we write it out. So ax equal b is equivalent in finding coefficients xi's such that this linear combination equals b. Now, so this poses some restraint if you want to have a solution or not. There would be a solution if this b vector is in the span of the column vectors, which means that b is in the column space of A. If that is the case, then there exists at least one linear combination that will represent this b. Okay. Therefore, we can say that this equation has a solution. The statement like that is equivalent to that the b is in the column space of A. There is another special space related to the A matrix. It's called the null space. It's the notation is this fancy n for null and of A. So this is the space of all vectors. Let's call the vectors the x. X is in Rn. It's all the vectors such that A times x equal 0 vector. So basically we form the problem ax equal 0, and we try to find all solutions to that. And all these solutions, they form a space we called a null space. Now here is an important claim. a property of the null space. So we claim that this space here is a vector space. So we need to show that it satisfies the properties of a vector space. And there are two things here. One is, if I have two elements x and x prime that's in the space, then the sum of these two is still an element in the same space. And furthermore, a scalar multiple of an element is also an element in the space. Okay, let's check that. So by assumption, the null space, if x is in the null space of A, then A times x is 0. And also x prime is in the null space, so A times x prime is 0. And then I want to show that x plus x prime is also in the null space. Then it's enough to show that A times x plus x prime, that equals 0. Okay, so let's look at this calculation. A times x plus x prime, so it's a vector, and plus a vector here, and then multiply by a matrix A. And I can distribute. I can multiply A on each of these vectors and then add them up afterwards. And then this first product give me 0, which is here. And the second product give me 0, which is here. And 0 plus 0 is 0. Okay, so that's what we wanted to prove. And the second property is to show Cx is in the null space. That is, I want to show A times Cx is 0. Okay, so what is A times Cx? Well, here C is just a scalar number. And then I can move it around. I can move it to the front or anywhere, or to multiply with it at the end. And then I can compute A times x first. And then A times x is just 0. And then any constant times the 0 vector is the 0 vector. Okay, so the two conditions for a vector space is satisfied. Therefore, the null space is a vector space. Okay, so let's take an example and very primitively try to find the null space of A. Now, given the A matrix like that, 2 by 3, the null space of A is all vectors x such that Ax is 0. This means I can write out what is Ax equals 0. So Ax is this A times x, and it needs to be a 0 vector. And let's try to find the solution. So we see that this A is already in the reduced row form, and then these two are leading entries, and we see that column 3 does not have any leading entrance, and therefore the x3 is arbitrary. Let's denote it by c, which is a parameter which can take any value. And then we solve for this problem. So once x3 is c, then we have x2, which is 2 times x3, and then move to the right hand side, you get negative, so negative 2c. Now to find x1, we can plug in the solution for x2 and x3 into the first equation and solve for x1. You can easily carry out this calculation, and you will find that x1 is 7c. So the solution here now, x1, x2, x3, will be 7c, negative 2c, and c. And we can take the c out and then write as c times this vector, 7, negative 2, and 1. Okay, so now we have the null space of A, which is a vector of this form with the parameter c, and then c is just any real number. So this is also the span of a single vector, which means any vector that's a linear multiple, scalar multiple of this is in this span. Okay, so now we need to use this to define the concept called the rank of a matrix. And let's go through a theorem first. So for any m by n matrix, we call it A. Then there is we can consider its row space, and we can consider its column space. and then each space will have a dimension. And the theorem says that the dimension R of the row space is the same as the dimension of the column space. And therefore this R is a very special number for the matrix A, and we call this R the rank of the matrix A. So R comes from the first letter of rank. And then we also know that the null space will have dimension n minus r. If r equals n, then the dimension is 0, and otherwise it's non-zero. And this number here is also called the nullity of a matrix A. Okay, so some fancy terms. So rank, dimension of null space is also called the nullity. Okay, so let's recall something we have learned earlier because they're useful here. So in the procedure of solving the linear system, we carry out this algorithm to put a matrix into a reduced row form. We remember, okay, so every matrix can be put into reduced row form by performing finite number of elementary operations, and the elementary operations are the following: multiply a row by a constant, switching two rows, and then add to one row a multiple of another. Okay, so here is the theorem related to that reduced row form. So let B now be a matrix in reduced row form. Let's say it's obtained from a matrix A by performing these elementary row operations. And then the following is true. The row space of B is the same as the row space of A, meaning performing a elementary operation does not change the row space. Okay. Second, the null space of B is the same as the null space of A. So remember the null space we just defined? It is actually defined in relation to the column space. Okay, so that's the column space, a subspace of it, where the element will make the solution AX equals 0. Okay. So a word of caution here is the first statement says the row space of B is the same as the row space of A. Now be careful. The column space of B does not equal to the column space of A. This statement is only for the row space. Okay. Okay, so let's take an example of that. So consider we have a matrix A, 3 by 4, which looks like this. And then we can perform these elementary row operations, which we'll go through very briefly. So you first make this element 0 by multiply it with 2 and add on top. And then you want to make this 0 by multiply this one by 3 and add on top. And then furthermore, you want to make this one 0 by multiply this by -1 and add on top. And then you have this matrix B, which is reduced row, in the reduced row form. And then we label the leading entries by put them in the block. Okay, so what is the row space of A? That's the span of the 3 row vectors, which we collect here. So it's the span of these 3 vectors. And the theorem says that this is the same as the row space of B, which is this vector here. What is the row space of B? Well, you only need to collect the non-zero vectors. That will be the first one and the second one. So it's the span of these two. And the theorem says these are the same. So, okay, so this span is exactly the same space as this span. Okay, then we know the rank of the A matrix, which is exactly the number of non-zeros and in the rows in B, because it's the rank of the B, which we see here is 2. Okay, so That's all for the part 1, and in part 2 we will take more examples and continue our study on this important concept of rank. Okay, so I hope you enjoyed this one, and I'll see you soon.